Welcome to another Daddy Pig seminar. This is part 3 of my SpaceGass for Dummies. And remember, the dummy is me. I've been stumbling my way through SpaceGass, trying to get to know it and its functions. And the learnings I've picked up along the way, I'm going to share with you. So we've done the basics in part 1 in terms of the interface, the buttons to press and so forth. Part 2, we saw how we put a frame together and analyze it and design the steel components, the members and connections and so forth. Part 3, we're going to be doing something a little bit different. This is pushing the realms of what SpaceGass can do, or at least I thought it was. What we've got on the screen now is the analysed version of a roof sheet. And this is a 2-span profiled roof sheet in steel. And so what we're seeing before us is the annotated version, so the coloured version for the stresses. Now my menus on the right are all hidden. So what is the legend here? So the legend, we click on the tab and it folds out. And so we have a range of stresses ranging from 75 MPa through to minus 134 MPa. And this is the load case for gravity. Okay, we switch load case for wind, uplift and gravity. We see the deformed shape here and we see the various stresses going from minus 302 to 537. So what have we got? Well, how did I get here? So I'm hiding the actual structure. So if I switch that on, that is the structure underneath. If I switch off the deflected shape, we go back to the flat profile. And again, if I switch off the contours, we go back to a simple shape. Okay, so this is the roof sheet profile. How did I get to that? Well, that is the rendered version. If we show the wireframe version, we have basically a series of beams. We've got a beam for each peak. So if I click, for example, on one member and look at the properties by clicking on the Properties tab, it looks like the usual arrangement, but I've defined sections in here. So SpaceGass allows you to define your own sections. And if you look at the section, the section or shape builder pops up. So this looks like a profiled roof sheet, or one rib of a profiled roof sheet. Now to build that, you can't either draw it yourself by putting in all the coordinates, but as you can see, that's an awful lot of coordinates. Or you can import from a DXF file. So I had the shape profile as a 2-dimensional CAD drawing. From that you export the DXF, and then into SpaceGass you can import the DXF file into here. So this gives you the basic shape properties. There's a button here marked Calculate Basic Section Properties, which basically does what you think it does. It calculates the basic section properties such as the area, the moments of area, and the offsets to the neutral axis, the torsional properties, and the section moduli, elastic and plastic, and derives the radius of gyration. There's another button which calculates the FEM section properties. So when you click that, it churns the handle once again and comes up with another set of properties that we can use as finite elements. Okay, you can actually add in design properties by clicking on the button at the bottom. And so we're telling you what kind of metal or material this is. So this is cold formed steel. It could be welded or it could be hot rolled. And you put in some basic parameters. So the normal strength and the high strengths for this particular grade all work out as 413 MPa. Okay, so we click OK to that. That defines the section for that element. I'll say no to that. Okay, so there's the basic properties, and we extend the beam all the way along. Now I've got 3 rows of support, so it's a 2-span continuous sheet, and so we have the end supports, which are basically effectively roller supports, and pin supports in the middle, and that gives you, as you can imagine, the typical bending moment distribution. If we click on the bending moment, so here we are for wind uplift. To make things simpler, I can click off the nodes. So there's your raw bending moment diagrams for each of those beams. That's for wind uplift. How about gravity loads? Similarly, it's that profile that you would get for vertical loading on the way down. If we want to look at the shear, click on the shear diagram, but switch off the bending moment, and they're pretty much as you suspect. So take them both off, and if we want to look at the deflection, click on the deflection button. If we want to make that a bit bigger, the trick is to hold down the D button and use your scrolling tool on your mouse. And there we have the deflected shape under gravity, and similarly with wind uplift. Obviously exaggerated a little bit there. Let's move that down. Okay, so that is the wireframe model. So you're probably wondering why I've done so many nodes. It, of course, is to keep the shape together. But if these were individual beams, you wouldn't get the deformation because they'd all deform individually as individual beams. So the way to make the beams work together is to use the master and slave node options. So we've put in all of these intermediate nodes along the beam, and then we've tied it to the master nodes here. So you'll notice that I've got lots of nodes here, and the nodes are connected together. The red square around each of these nodes indicates that they're a master node. If I select one of those nodes and click out properties, it has the usual facilities there, and the constraint, it says the constraint is none. So if I escape from that and select another node, look at the properties of that, then I've now got a constraint, and so it's a pin-to-pin restraint. So if node 49 goes down, then node 50 goes down with it, and similarly node 51 and node 52, and then we repeat the process. So how did we get to that? Let's escape from that and look at a plan. Okay, so one way of doing it is to select the nodes. We can drag and select, click on the properties, and in here we've got the constraint tool, but you also need to select the node master. By clicking on that, you can select the node master. So it shows you that node 10 is the master. I can select a different node by simply selecting another node. So now it's node 11. To maintain that 11, node 11 as the master node, you click OK. If I click on revert, this will revert the data that you have changed and go back to the previous position. And that's it, it's as simple as that. So now when we load it up, so we've got our loads shown here, and this is for wind uplift. We've got a similar one for dead, we've got a similar load case for live, and these are all considered as uniformly distributed loads, basically beam loads, and we can get to that by clicking on the data set for the load. So there's node load, no, they're member distributed forces. So using the loading tools in SpaceGass, we're able to define loads in a particular direction. In this case, it's the Y direction with a particular size for each of the members. And for this case, load case 1 happens to be dead, If you scroll through, we've got 2, which is live, and then 3 is the wind uplift. So we'll close that. As usual, we click on Analyze to do our linear static analysis, and it will then give you the results. So coming back to the results, let's take the loads off. So your bending moments again. Now we want to do something special, the member stresses. Well, you can't really see the member stresses as a wireframe. So let's render it. And now if we do the member stresses, what do we want? So we want bending stress at the top. It's usually the critical one. If we click OK. So we've selected the member bending stresses at the top. So our legend here is for live load. Similarly, if you want the wind uplift, it'll reverse it. Scroll out to see a better picture of that. And similarly with ULS gravity. So that was the bending stresses based on the beam. Now, we can trick it into thinking it's member contours. And in member contours, you've got contour preferences. And there's a whole range of things you can do. Now, everybody goes through the von Mises stresses, which is basically a combination of the principal stresses and the shear stresses. This is what many engineers use as the definitive overall stress. But von Mises stresses are not the only stresses. You can do the bending stresses directly, principal stresses or shear stresses, should you wish. You can change the color range as you wish. So if I click OK, let's have the bending stresses on there. So for the gravity load case, we've got the color scheme going from red for 75 MPa positive through to blue as negative. So for ULS gravity loads, let's make that a bit bigger. For ULS gravity loads, we've obviously got tension stresses over the central support. Now, if we reverse that by using our wind uplift, we've now got compression stresses at the top for our wind uplift case. To make it a bit more impressive, you can click on the deflected shape. And to clean it up a little, you can switch off the nodes and you can switch off the frame itself. And there we have pretty pictures to put in your report. As usual, your output can be graphical and it can be text report. So that was a way of analysing a roof profile as a series of beams given an imported DXF file of a basic shape of that roof. So that's part 3. In part 4 we'll look at plates, and this is where it gets quite interesting.